Imagine this. Somewhere above you, high on a mountain or deep inside a quiet national laboratory, there is a box the size of a suitcase. It doesn't look like the beating heart of modern civilization. No glowing blue core, no humming sci-fi coils, just cables, polished steel, a vacuum chamber, and layers of insulation that shield its contents from even the faintest temperature change. Inside that unremarkable box, clouds of cesium-133 atoms drift through carefully tuned magnetic fields and laser beams. Their electrons flip between two hyperfine energy states, an incredibly small transition in the structure of the atom that produces a burst of microwave radiation. When those atoms switch states exactly 9,192,631,770 times, we declare that 1 second has passed. That number isn't poetic, it isn't symbolic, it is the exact definition of the modern second, adopted internationally in 1967, when it became clear that Earth's rotation could no longer serve as a stable foundation for precision timekeeping. Atomic transitions, governed entirely by the laws of quantum mechanics, are vastly more consistent than the behavior of a rotating planet stirred by tides, winds, molten iron, and shifting oceans. And yet we live on that planet, and it refuses to spin at a perfect rate. Its rotation speeds up, it slows down, it drifts, it wobbles, sometimes by predictable amounts, and sometimes by amounts large enough to force scientists to update models, reanalyze data, and rethink long-standing assumptions. When these two clocks, the atomic one and the planetary one, grow far enough apart, humanity is forced to intervene. We adjust the global time scale, we add a second, and soon we may have to remove one. Before we go deeper, if you enjoy sinking into these scientific journeys, where abstract physical principles become deeply human considerations, consider subscribing to Sleepless Knowledge and leaving a comment with where you're listening from and what time it is there. It helps this channel grow and it keeps these quiet explorations alive. Now let's widen the frame. For most of human history, the length of a day was simple, one rotation of the Earth. That rotation was divided into 24 hours, each hour into minutes, each minute into seconds. Every sundial, every medieval bell tower, every early mechanical clock depended on Earth spinning at a steady pace. But by the 19th century, astronomers noticed something deeply unsettling. Careful measurements of star positions, planetary transits, and eclipse timings revealed that the Earth's rotation is not constant. The length of a day varies by milliseconds. A human blink is about 100 milliseconds. The changes in Earth's rotation are thousands of times smaller, yet absolutely real. To understand why, we need to peel back the physics. The longest-term effect is tidal friction. The moon's gravity pulls on Earth's oceans, raising bulges of water. Because Earth rotates faster than the moon orbits, those bulges are dragged slightly ahead of the Earth-Moon line. This misalignment pulls back on Earth's rotation, gradually slowing it while pushing the moon outward. Over hundreds of millions of years, this lengthens the day. In the distant past, a day may have lasted roughly 22 hours. But that's just the slow geological trend. On much shorter timescales, years, months, even days, Earth experiences rotational fluctuations caused by atmospheric angular momentum, ocean currents, and mass redistribution across the surface. When vast air masses accelerate around the globe, or when deep ocean currents shift, the solid Earth adjusts slightly, conserving angular momentum. These exchanges can change the length of a day by fractions of a millisecond. Large earthquakes can also produce measurable changes. The sudden reshaping of mass inside the planet during a major rupture, like the 2004 Sumatra-Andaman earthquake, shortened the length of the day by a few millionths of a second. It sounds tiny, but at the level required for satellite navigation and planetary-scale communication networks, it is significant. Even melting ice plays a role. When glaciers melt and water flows toward lower latitudes, the planet's moment of inertia increases, similar to a spinning figure skater extending their arms. The rotation slows slightly. When ice accumulates closer to the poles, the opposite occurs. All these processes combine into a rotation that is always drifting. And then there is the wobble. Earth does not spin like a perfectly centered top. Its axis slowly traces a large circle in space over roughly 26,000 years, a motion called precession. On top of that, gravitational tugs from the moon and sun create smaller oscillations known as nutation, and layered over both is the Chandler wobble, a free oscillation of the poles with a period of about 14 months. These motions cause the geographic poles to move in small circles of a few meters on the Earth's surface. Sensitive instruments, such as radio telescopes using distant quasars as fixed beacons, can detect this wobble and measure how it alters the exact length of each rotation. Modern timekeeping relies on two timescales: TI, International Atomic Time, a continuous count of atomic seconds, UT1. Earth rotation time, defined by the actual spin of Earth. UTC, Coordinated Universal Time, the civil time scale that blends the two. TI flows with perfect consistency. UT1 wanders. UTC tries to stay aligned with the sun, remaining within about a second of UT1 so that noon still corresponds to the middle of the day. But because Earth doesn't behave, UTC sometimes needs a correction. The leap second. When Earth falls behind atomic time, we add 1 extra second at the end of a day. It's a tiny, artificial pause that keeps human time close to the sky. Since 1972, 27 leap seconds have been inserted by the IERS, the International Earth Rotation and Reference Systems Service. But in recent years, Earth has been rotating slightly faster than expected. Some of the shortest days in modern history have occurred in the past decade, and if that continues, we may soon face something we've never done before: a leap second removed instead of added. Not an extra heartbeat inserted into the world's clocks, but a heartbeat skipped, a moment that would simply vanish. A day that would end 1 second sooner than it normally would. Time, for the first time in human history, would jump forward by a second. That is where this journey leads. But before we reach the complexities of negative leap seconds, digital failures, global politics, and the gradual abandonment of leap seconds altogether, we need to travel further into the physics shaping our unsteady world, and the reasons humanity had to start negotiating with a wobbling Earth in the first place. Time feels simple when you're living inside it. You look at a clock, and the hands move with such clean intention that it's tempting to believe time itself is something natural, something the universe produces in neat, evenly spaced pieces. 1 second, then another, like footsteps echoing in a hallway. But what a second truly is a much stranger story. It's a story that begins with the motions of celestial bodies, passes through centuries of astronomy, travels into the heart of physics, and ends up inside a metal vacuum chamber where atoms drift in a silence so perfect that even the faintest vibration could ruin the measurement. It's also a story about what we choose to trust, the sky above us, or the atoms within our instruments. And buried inside that choice is something emotional, something almost philosophical. Because at some point in the 20th century, humanity decided to abandon the sky as its master clock and hand that responsibility to an arrangement of electrons inside a rare metal atom. For thousands of years, the idea that time could be defined by anything other than the heavens would have sounded absurd. Let's walk into that shift slowly. For most of human civilization, a second was simply a fraction of something larger, a slice of a day. The Earth spins once every 24 hours, so you divide that rotation into 24 hours. Divide those hours into 60 minutes, and those minutes into 60 seconds. That was the logic. People didn't choose the second because of a physical law. It was just arithmetic built on top of the world, turning beneath them. Everyone knew that days weren't identical. Some were a bit longer, some a bit shorter, but there was no practical way to measure the difference. If your clock wandered by several minutes a day, which many early clocks did, there was nothing in your experience to suggest that the planet itself was shifting under your feet. Sundials marked noon by the sun's shadow. Water clocks measured flow. Sand clocks measured gravity dragging grains downward. None of them were precise. None of them needed to be. But astronomy changed everything. By the 17th and 18th centuries, telescopes enabled astronomers to observe planets and stars with far greater accuracy than ever before. And as astronomers tried to predict the motions of the heavens using Newton's laws, they noticed something subtle. When they used Earth's rotation as the reference for time, the predictions weren't perfect. The discrepancies weren't because Newton was wrong. They were because Earth itself wasn't a reliable clock. But this insight took generations to deepen. By the late 19th century, the field of geodesy, precise Earth measurement, was producing remarkably sophisticated observations of star transits across the sky. These measurements revealed little irregularities. Some days were slightly longer than others, and these variations didn't follow a predictable pattern. It was as if the Earth were breathing, its rotation quickening and slowing in gentle, uneven pulses. But a second was still defined as 1/86,400th of the mean solar day. That definition made sense historically, but it meant that the second was essentially tied to a wobbling, unpredictable reference. The problem remained manageable, until humanity created machines that required much more accuracy than the planet offered. In the early 20th century, new technologies began to demand better timekeeping. Radio communication needed synchronization. Navigation depended on precise timing. Physics experiments, especially those exploring the structure of atoms and light, relied on measurements far more delicate than astronomical time could provide. Imagine trying to measure the speed of light or the energy of an electron transition using a second defined by the motion of an entire planet sloshing with tides and stirred by atmospheric winds. It's a bit like trying to read fine print on a page while sitting on the deck of a ship rocking in the waves. You can, technically, but it's not ideal. Scientists realized they needed a definition of the second that didn't depend on Earth's rotation, something more stable, something grounded in the fundamental physics of matter itself. This wasn't just a practical shift, it struck at something deeply symbolic. We were about to stop using nature's clock and instead create our own, one forged not by the sky, but by the structure of atoms. The question became, where in the universe can we find something that ticks with absolute regularity? And the answer emerged from quantum mechanics. The early 20th century saw the rise of quantum theory, and with it came an understanding of how atoms behave. Electrons inside atoms occupy discrete energy levels. When they jump between these levels, they emit or absorb radiation with frequencies governed by fundamental constants. These frequencies are astonishingly stable. Unlike the rotation of a planet, which depends on a swirling mixture of rock, water, and molten metal, the frequency of an atomic transition is the same everywhere in the universe. That makes atoms ideal candidates for timekeeping. Scientists began experimenting with ammonia molecules in the 1940s, and then with cesium atoms in the 1950s. Cesium-133 in particular has a hyperfine transition that emits microwave radiation at an extremely consistent frequency. Early cesium clocks were bulky and experimental, but they demonstrated something important. Atomic clocks could outperform the finest astronomical timekeeping. By the 1950s, the gap was undeniable. Astronomical time wandered, atomic time did not. The idea of defining the second based on an atom instead of Earth's rotation moved from radical to inevitable. In 1967, the definition officially changed. A second was no longer tied to the length of a day. It became the duration of 9,192,631,770 cycles of the microwave radiation emitted by the hyperfine transition of cesium-133. The actual number isn't meant to be memorized in everyday life, but the concept matters deeply. The second is now rooted in the quantum structure of matter, in a phenomenon that is the same whether you measure it in Paris or Tokyo today or 1,000 years from now, but shifting to atomic time created a philosophical tension that we still live with today. On the one hand, atomic time, International Atomic Time or TI, is perfect for physics. It's uniform, it's stable, it never surprises us. On the other hand, Earth rotation time, known as UT1, is the time our planet actually produces. It's tied to the rising and setting of the sun, to the rhythms that shaped life for billions of years, and to the instinctive way humans understand the passing of a day. And these two timescales drift apart, not quickly, not dramatically, but steadily. If atomic time and Earth time weren't reconciled, the noon on your wristwatch would slowly drift away from the moment the sun is highest in the sky. It would take centuries for the drift to accumulate to something noticeable. Minutes first, then hours. But eventually, clocks and sunlight would disagree in ways that felt deeply wrong to human experience. This is why we created UTC, Coordinated Universal Time, a compromise built on atomic seconds but occasionally corrected by a leap second to stay close to Earth. It's a negotiation, a truce between our technological needs and our biological, astronomical heritage. But the moment we defined time using atoms instead of the sky, something subtle happened to our relationship with nature. For almost all of human history, we lived inside nature's clock. Time was something the world produced. We followed it. Now time is something we define, and the world must keep up. There's something both empowering and unsettling about that. It is scientific progress, but it also marks a turning point. Timekeeping has moved from the cosmic to the human-made, from celestial mechanics to quantum physics. When we abandoned Earth's rotation as the heartbeat of time, we didn't just change how clocks work, we changed our place in the story. We stopped keeping time by watching the sky, and instead began keeping time by listening to the whisper of electrons inside a single atom. And from that moment on, the wobble of Earth became a problem, an irregularity that had to be corrected, compensated, or eventually ignored. How we chose to deal with that wobble, and how the leap second was born, forms the next step in this journey. If you stand outside at night and watch the stars drift across the sky, it's easy to imagine that the Earth spins with machine-like precision, turning smoothly, evenly, predictably. The calm arc of the constellations gives the illusion that our planet's rotation is a perfect rhythm, something stable enough to build clocks around. But beneath that quiet, graceful motion lies a truth that's far more complex. Earth's rotation is irregular, it shifts, it fluctuates, it reacts to forces inside and outside the planet, turning each day into something slightly different from the one before. A day is never exactly 24 hours long. That number is an average we use because it makes life simple, but the real length of a day can vary by fractions of milliseconds. These variations are tiny, far smaller than anything a human could feel, but they accumulate and they reveal how dynamic our planet truly is. The idea that Earth's rotation might not be constant seems strange at first. After all, it's an enormous sphere of rock. How could something so massive behave in such a delicate way? To understand it, you have to imagine the Earth not as a rigid spinning ball, but as a layered, moving, shifting system where the atmosphere, oceans, and molten core all trade angular momentum with the solid crust. Some changes are slow and gradual, others are sudden and sharp, and some are so long-term that you would never notice them in a lifetime, yet they shape the evolution of the planet over millions of years. The slowest and most persistent of these forces is the gravitational pull of the Moon. The Moon raises tides in Earth's oceans. Because Earth rotates much faster than the Moon orbits, those tidal bulges are pulled slightly ahead of the Earth-Moon line. That misalignment acts like a brake. It drags on Earth's rotation and transfers energy to the Moon, pushing it outward by roughly 3.8 centimeters per year, which is about 1.5 inches. This process, tidal friction, has been happening for billions of years. In the distant past, the day was significantly shorter. Hundreds of millions of years ago, the planet completed a full rotation in about 22 hours. Go back even further in time, and the day gets shorter still. This long-term slowing is only one part of the story. On much shorter timescales, day by day, month by month, year by year, the atmosphere plays a major role. Air masses carry enormous angular momentum. When jet streams speed up or slow down, when trade winds shift, when high-altitude winds accelerate around the globe, the solid Earth responds. If the winds push more atmosphere eastward, Earth's rotation slows slightly. If the winds weaken or move westward, Earth speeds up. These changes can alter the length of the day by milliseconds. Tiny amounts, but large enough to track with modern instruments. The oceans do something similar. Their currents, tides, and global circulation patterns shift colossal amounts of water around the planet. Deep currents flow thousands of kilometers, and when these water masses redistribute themselves, they change the rotation ever so slightly. Events like El Niño and La Niña have measurable effects on the rotation rate because they rearrange heat, air pressure, and oceanic mass across the Pacific. Then there's the molten iron outer core, swirling and churning beneath the crust. The core and mantle don't rotate perfectly in sync. Magnetic and viscous coupling between them allows tiny exchanges of angular momentum. Over years and decades, these internal motions alter the rotation. They're subtle and mostly invisible from the surface, but they show up in the length of the day when measured by atomic clocks and radio astronomy. Some changes in Earth's rotation happen suddenly. Large earthquakes can shift mass inside the planet abruptly. When the 2004 Sumatra-Andaman earthquake struck, one of the most powerful earthquakes ever recorded, it caused a redistribution of mass that shortened the length of the day by a few microseconds and shifted Earth's axis by several centimeters. These effects are tiny but real, and they demonstrate how sensitive the planet's rotation is to changes in the distribution of mass. Even the melting and freezing of ice affects the length of the day. During the last ice age, massive ice sheets weighed down the continents. When that ice melted, the crust slowly rose back up, a process called glacial rebound. As land lifts and shifts, mass redistributes, changing Earth's moment of inertia. It's the same principle as a figure skater who extends their arms to slow down or pulls them in to speed up. The Earth is still adjusting from the end of the last ice age, and that process continues to subtly modify the planet's rotation. You can see the effect today in areas like Canada and Scandinavia, where the crust is still rising by centimeters per year, small motions, but enough to slightly influence the rotation. Modern ice melt from Greenland and Antarctica has its own influence. As meltwater flows toward the equator, it shifts mass outward, slowing Earth's rotation just a little. These slow adjustments create long-term trends in the length of the day. But how do we know all this? Because humanity has been watching the sky with increasing precision for thousands of years. Ancient civilizations recorded eclipses with remarkable detail. The Babylonians, the Chinese, the Greeks, and many others documented the timing and location of eclipses across centuries. When modern astronomers compare those records with precise modern calculations of where the Earth and Moon should have been, they find a mismatch, a sign that Earth's rotation has slowed over millennia. The evidence becomes even clearer in the modern era. Quartz clocks in the early 20th century and later atomic clocks revealed fluctuations in the length of the day that would have been impossible to detect earlier. With radio telescopes measuring Earth's orientation relative to distant quasars, scientists can measure rotation variations with extraordinary accuracy, down to microseconds. What they found is that Earth's rotation is not stable in any strict sense. It is dynamic, interactive, and continuously shifting. Seasonal variations cause predictable patterns. The day length shortens slightly in one season and lengthens in another due to atmospheric circulation patterns. Decadal variations appear as ocean and air currents shift globally. Long-term trends emerge from glacial rebound and tidal friction, and sudden jumps happen in the aftermath of large earthquakes. And this is why we need leap seconds, why the perfect, steady beat of atomic clocks must occasionally be adjusted to stay aligned with a planet that refuses to turn at a constant rate. The Earth is not a machine. It is a restless world of moving air, flowing water, shifting crust and liquid metal. Its rotation carries the memory of ancient tides, atmospheric storms, volcanic eruptions, and even the lingering effects of the last ice age. Every tiny change in that rotation eventually shows up in our clocks. Every wobble, every shift, every exchange of angular momentum moves us closer to, or farther from, needing another correction. Understanding these variations brings us closer to understanding why time itself, at least the time we use to organize human life, must sometimes be corrected. And it leads directly into the next layer of this scientific puzzle, the wobble of Earth's axis, the way the poles drift, and how these motions tie into the story of leap seconds. If you close your eyes and picture the Earth spinning in space, you might imagine a perfect rotation, a smooth, steady sphere turning around an unmoving axis like a flawless gyroscope drifting through the void. But the real Earth refuses to behave so neatly. Its axis shifts, loops, nods, and trembles in motions that unfold over months, years, centuries, and entire ages. These motions are subtle, far too subtle to feel, yet they shape how the Earth is oriented in space and leave faint signatures on the length of each day. To understand these movements, imagine the Earth not as a rigid ball, but as a layered, fluid, dynamic system. Oceans flow, winds push, continents drift, and deep beneath the crust, a core of molten metal churns. All of these layers respond to the gravitational pull of the moon and the sun. The result is a series of oscillations, predictable in some cases, mysterious in others, that create a complex dance in the orientation of the planet. The largest of these motions unfolds over an immense span of time. This is precession, a slow rotation of Earth's axis that takes about 26,000 years to complete. Earth's axis is tilted at roughly 23.4 degrees relative to its orbit around the Sun. Because Earth isn't a perfect sphere, it bulges slightly at the equator. The gravitational pull of the Sun and Moon tugs on that bulge. This creates a torque that tries to straighten Earth's tilt. The rotation of the planet resists that straightening, and the result is a slow, circular drift of the axis. If you could watch Earth's axis from a fixed point far away, you would see it trace a giant, gentle circle in the sky. This is why the identity of the North Star changes over time. Today, the axis points near Polaris. Thousands of years ago, it pointed near Thuban in the constellation Draco. Thousands of years from now, it will point near Vega. Precession shifts the entire coordinate grid astronomers use, changing the backdrop of the heavens over millennia. Layered on top of this long cycle is another motion called nutation. Nutation is caused mainly by the Moon's gravitational pull, with contributions from the Sun. The Moon orbits Earth on a path that is tilted and slightly elliptical. As the Moon moves closer or farther away or passes above or below the Earth's equatorial plane, the gravitational torque on Earth's equatorial bulge changes. The effect is a periodic nodding of the Earth's axis. The dominant nutation cycle lasts about 18.6 years, tied to the slow shifting of the Moon's orbital nodes. It changes the tilt of the axis by small amounts, fractions of a degree, but enough to matter for precise astronomical observations. Smaller oscillations ride on top of the main one, produced by annual and semi-annual gravitational alignments of Earth, Moon, and Sun. If precession draws the broad circle, nutation draws the gentle ripples along its edge. If you sped up time by thousands of times, you would see the axis drawing looping, spiralling patterns rather than a single clean circle. The wobble becomes even more intricate when considering a phenomenon discovered by Seth Carlo Chandler in the late 19th century. By carefully observing the positions of stars night after night, he noticed that the Earth's poles were not fixed. They wandered in a small circular pattern with a period of roughly 14 months. This tiny motion, only a few meters across at the surface, became known as the Chandler wobble. Its cause was not immediately clear. It didn't match the wobble predicted by simple physics for a rigid spinning body. The Chandler wobble indicated that Earth's interior wasn't rigid. Something inside the planet was interacting with the rotation in a way that changed the axis of spin. Today, we know that the wobble is influenced by both the molten outer core and the movement of massive fluids, air in the atmosphere and water in the oceans. These systems exchange angular momentum with the solid Earth, adding energy to or removing energy from the wobble. One of the most intriguing events in recent geophysical history occurred around 2017 when the Chandler wobble suddenly weakened. Its amplitude dropped sharply, surprising researchers who monitored Earth's rotation. The wobble almost faded into the background before gradually reasserting itself in the following years. The cause of the weakening remains under study, but many scientists point toward unusual patterns in atmospheric pressure and ocean circulation during that period. Those shifts may have temporarily interrupted the flow of energy that normally sustains the wobble. These movements of Earth's axis aren't just academic curiosities, they have practical consequences. Modern navigation systems, satellite operations, and space missions all depend on precise knowledge of how Earth is oriented in space. Very long baseline interferometry, which uses widely separated radio telescopes to track distant quasars, measures tiny changes in Earth's orientation with exquisite accuracy. Shifts of a few meters at the poles translate into important adjustments in the mathematical reference frames that underpin global positioning. The wobble also leaves faint signatures on the length of the day. Most of the variation in day length comes from exchanges of angular momentum between the atmosphere, oceans, mantle, and core, but slight contributions come from changes in Earth's orientation as well. These changes are extremely small, fractions of a millisecond, but they accumulate when comparing Earth rotation time with atomic time. All of these wobbling motions, whether they take 14 months or 26,000 years, tell the same story. The Earth's axis is not fixed. It is shaped by the combined forces of gravity, internal structure, fluid motion, and orbital mechanics. The planet is constantly adjusting, shifting, and responding to the forces acting upon it. The axis traces loops, the poles drift, the tilt nods, the rotation responds in kind. Seen from a cosmic distance, these shifts are subtle. Seen through the lens of modern instruments, they are finely detailed motions that scientists can track with astonishing accuracy. They reveal a world that is not stiff or static, but flexible and responsive. And all of these motions, the great sweep of precession, the graceful nod of nutation, the small but persistent 14-month circle of the Chandler wobble, combine to shape the true nature of Earth's rotation and the delicate balance that keeps our clocks aligned with the sky. Humanity has always needed time, not just to mark the rhythm of days and nights, but to organize movement, to navigate, to communicate, to understand the physical world. For most of our history, the imperfect rotation of the Earth was precise enough. If the dawn arrived a little earlier or a little later from one season to the next, nobody cared. Life was local. Travel was slow. Communication travelled no faster than a horse or a ship. But the world changed, slowly at first, then all at once. The moment humans began crossing oceans with accuracy, timing became a matter of survival. A ship at sea needs to know its longitude, and longitude is impossible to determine without precise time. Latitude comes from the sun's height. Longitude comes from comparing the local time with the time at a fixed reference point. If your clock drifts even a bit during a long voyage, you drift with it, hundreds of kilometers off course, sometimes into reefs, storms, or entire continents you never meant to see. This was the great challenge of the age of exploration. Navigators could measure angles in the sky with impressive skill, but they were helpless without a stable reference clock. Pendulum clocks failed aboard ships, swaying with the waves. Balance wheel clocks drifted too much. The race to build a marine chronometer consumed decades. It was an engineering challenge tied directly to the rotation of Earth itself, and it revealed something uncomfortable. Earth's rotation could not provide the precision humans increasingly demanded. Yet even the marine chronometer was only the beginning. When the telegraph arrived in the 19th century, cities found themselves needing synchronized clocks for the first time. A message sent from Paris to London required both cities to agree on what time it was. Train schedules demanded that entire regions share a unified system of hours and minutes. Local solar time, where noon was simply when the sun crossed the local meridian, became impossible to use in a world connected by wires, rails, and commerce. This led to one of the most consequential decisions in human history: the establishment of a single prime meridian at Greenwich in 1884 and the adoption of standardized time zones. For the first time, the world agreed that time could be something coordinated, unified, shared, a collective human construction rather than a purely astronomical fact. But even after time zones became standard, the deeper issue remained. Earth does not rotate steadily enough to be used as the ultimate reference for precision. Astronomers could measure the irregularities, but they could not compensate for them easily across continents. And for most practical purposes, the irregularities were small enough that nobody felt their impact. Then came the mid-20th century, when science and technology reached a level of precision that nature simply could not satisfy. Radio communication demanded microsecond accuracy. Long-distance telephone networks required perfect synchronization to avoid echoes, delays, and dropped connections. Radar systems, used for both aviation and defense, depended on exact timing to measure distances and velocities. High-speed computation was emerging, and with it a need for clocks that did not wander. And above all these technologies stood the satellites. When the first artificial satellites were launched in the late 1950s, the Earth changed forever. Suddenly, signals could fly around the world in a fraction of a second. Navigation from orbit required knowing exactly where a satellite was, exactly how fast it was moving, and exactly how long its signals took to reach receivers on the ground. Even a tiny error in timing translated into hundreds of meters of error in position. This was the birth of something astonishing. A world where time had to be precise across continents, oceans, and eventually the entire planet. And the Earth itself was the problem. Scientists could see that the rotation of the planet was drifting unpredictably, sometimes lengthening the day, sometimes shortening it, depending on winds, currents, seasonal variations, and deep interior motions. Meanwhile, new devices, atomic clocks, were demonstrating something extraordinary. They were stable in a way no natural process could match. Atomic clocks did not care about tides, storms, or molten iron. Their accuracy depended only on the structure of atoms and the unchanging laws of quantum mechanics. They could keep time with such perfection that their drift over millions of years would be measured in seconds. By the 1960s, the contrast between Earth's rotation and atomic timekeeping was undeniable. The old definition of the second, tied to the motion of the planet, was no longer adequate. Scientists needed a time scale that was stable, smooth, and immune to Earth's wobble. Technology demanded it. Physics demanded it. And so the world made a decision that quietly transformed civilization. Time would no longer be anchored to the motion of a planet. It would be anchored to the rhythm of atoms. International Atomic Time, TIE, was created as a purely atomic timescale. It counted one atomic second after another, with no reference to the rising and setting of the sun. TIE became the backbone for scientific and technological applications that needed unwavering precision. But this created a new problem. TIE did not match civil time anymore. If TIE was allowed to run unchecked, Noon on a clock would slowly drift away from the actual position of the sun, at first by fractions of a second, then by seconds, then minutes. Eventually, noon would arrive when the sun was nowhere near the middle of the sky. People do not live according to atomic time. They live according to sunlight, seasons, and a biological sense of day and night. Time was perfect, but it was not human. Something else was needed. A time scale that used atomic seconds but stayed close to Earth's rotation so that human experience did not drift away from nature. This was the birth of Coordinated Universal Time, UTC. UTC blends the stability of atomic time with the irregular beat of Earth's rotation. It's built from atomic seconds, but it is occasionally adjusted with leap seconds to keep it within about 1 second of UT1, the time defined by Earth's actual rotation. TI and UTC are profoundly different. TI is pure physics, a relentless stream of identical atomic seconds. UTC is a compromise, a human timescale that stays in step with the sky. This split revealed something remarkable about our species. For the first time in history, humanity maintained two different versions of time, one based on nature, one based on our own instruments, and between them lies a philosophical divide. The atomic second is an abstraction born of quantum mechanics. It is the same everywhere in the universe. It makes no reference to Earth, sunlight, or the cycle of days. It is universal in a way that the ancient astronomers could never have imagined. The rotational day is ancient. It is the rhythm life evolved under. It is the pulse that guided agriculture, religion, navigation, migration, and the structure of every human society for thousands of years. UTC is the bridge between these two worlds. It keeps human society anchored to the sun while allowing science and technology to rely on the perfection of atoms. And yet, this solution came at a cost. It required acknowledging that Earth's rotation is too unstable to serve as the foundation of time. There is something quietly profound about this. After millennia of looking to the sky to tell the hour, humanity turned inward to the quantum properties of matter to define the most fundamental tick of time. We replaced nature's clock with a human-made one. We chose precision over tradition, stability over familiarity. The creation of UTC was not just a technical decision, it was a declaration that the universe's rhythms are not always precise enough for our ambitions. It was a moment when human invention became more reliable than the planet we live on. UTC, with its leap seconds, became the compromise that lets us keep both. The elegance of atomic precision and the comfort of knowing that noon is still roughly when the sun is highest. It is a balance between two competing truths, that nature is beautiful but imperfect, and that human technology is precise but emotionally detached from the rhythms we evolved under. This balance defines modern timekeeping. It defines the way satellites operate, the way data flows, the way global systems communicate. It is one of the quiet foundations of modern civilization, almost invisible, yet essential. And it exists only because the Earth, for all its beauty, refused to turn at a constant pace. By the late 1960s, the tension between atomic time and Earth rotation time had grown too large to ignore. Atomic clocks marched forward with perfect consistency while the Earth wandered, sometimes slowing down, sometimes speeding up, drifting unpredictably by milliseconds from year to year. Technology could no longer tolerate this mismatch. Satellites, global communication networks, and scientific instruments relied on timing precise down to millionths of a second. Yet civil society expected noon to remain roughly when the sun reached its highest point in the sky. These two expectations collided, and something had to give. The world needed a timescale that could satisfy both the physicists and the public, the satellites and the sailors, the engineers and the ordinary clock on the wall. It needed something stable, yet flexible, something atomic, yet still connected to the turning planet. The solution was ingenious. and strange. The leap second. The idea of inserting a second into the world's clocks, like slipping an extra heartbeat into a day, was new and controversial. But before it could be implemented, the scientific community had to agree on how to reconcile two competing systems. Ti, which flowed smoothly and perfectly, and UT1, which reflected Earth's actual rotation but wandered unpredictably. Throughout the 1950s and 1960s, there were disagreements among physicists, astronomers, timekeeping authorities, and national standards agencies. Some argued that atomic time should completely replace Earth-based time. They claimed that civil time should rely entirely on cesium oscillations and abandon any reference to the planet's rotation. After all, atomic clocks were far more stable than anything nature could offer. Others insisted that humans live by the sun, not by atoms. Noon should remain tied to the sky, not to laboratory instruments. They feared that abandoning Earth-based time would disconnect society from the rhythms humans had followed for millennia. Both sides were right, in different ways, and neither wanted to compromise. Scientific debates became philosophical debates, conferences were held, papers were written, national agencies lobbied for their preferred systems. The United States favoured a transition to fully atomic time. British and European astronomers argued strongly that civil time must remain aligned with Earth. All the while, the gap between atomic time and Earth time continued to grow. The mismatch was not dramatic at first, a fraction of a second here and there. But over years, the difference accumulated. If nothing was done, the clocks on Earth would drift away from the position of the sun, eventually producing a world where midday might occur at an emotionally alien hour. By the early 1970s, the need for a decision became unavoidable. In 1972, a major agreement finally emerged. The solution was Coordinated Universal Time, UTC, a hybrid system that used atomic seconds but was anchored to the planet through occasional corrections. To keep UTC aligned with Earth's rotation, a newly created international organization, the International Earth Rotation Service, IERS, was tasked with monitoring Earth's rotation with extraordinary precision. The IERS measured the difference between UTC and UT1, the timescale that reflects Earth's actual rotation. When that difference approached a threshold, about 0.9 seconds, the IERS would declare that a leap second was required. This second would be added to the final minute of the day, a minute that would briefly have 61 seconds. It was an elegant solution. Time would continue flowing onward, uninterrupted. UTC would remain practical for daily life, and Earth-based time, UT1, would no longer directly define the second, but would still help determine when adjustments were necessary. It was a bridge between the quantum and the astronomical, between human experience and physical precision. But the decision to adopt leap seconds wasn't unanimous. Some scientists felt uneasy about the idea of modifying the length of a minute, letting 1 minute occasionally last longer than another. They argued that timekeeping should be as uniform as possible, and the leap second introduced irregularity. The very concept defied the simplicity people expected from clocks. Others embraced it as a natural compromise. Earth was messy, and leap seconds were simply a way to acknowledge that messiness without allowing it to disrupt the global system. When the decision became official in 1972, there was a unique moment in the history of time. The modern timekeeping world had split into two synchronized but different systems: Ti, which counted atomic seconds endlessly, and UTC, which followed atomic time, except for those occasional moments when Earth reminded everyone that it wasn't spinning perfectly. The first leap second was added on June 30th, 1972. At the end of that day, clocks paused for 1 extra second. The time went from 23:59:59 to a kind of suspended moment, an inserted beat before rolling over to midnight. Most people didn't notice anything. Their watches ticked as usual. Clocks on kitchen walls moved forward without hesitation. The world didn't stop or stutter in any perceptible way. But to those who monitored time, Meteorologists, astronomers, navigators, telecom engineers, it was a historic event. It was the first time humanity had deliberately intervened in the flow of time across the entire planet. It wasn't a calendar change, like skipping days when switching between systems. It wasn't a time zone change. It was a modification of the fundamental length of a minute. It was a tiny correction invented to keep Earth and atoms in harmony. More leap seconds followed. Throughout the 1970s, several had to be added because Earth's rotation continued to lag behind atomic time. The drift was expected, but its exact behavior was unpredictable. The IRs monitored the rotation constantly using techniques such as very long baseline interferometry, laser ranging, and satellite-based geodesy. These methods revealed that Earth's rotation could wander more than previously believed. Scientists analysed the pattern of the leap seconds and began to understand more about the complex factors influencing Earth's rotation. Atmospheric pressure changes, oceanic currents, the dynamic behaviour of the core and mantle, and even the exchange of water from melting ice sheets into the oceans. Each leap second became a marker of how the planet was behaving. A leap second wasn't just a correction for clocks, it was a piece of geophysical evidence. As leap seconds accumulated, the world slowly became aware that timekeeping was more complex than anyone imagined. News stories occasionally mentioned the leap second, describing it as a curious oddity, the day with an extra second. For many people, it sounded like a tiny gift, a bonus moment slipped into existence for no particular reason. Others found it unsettling. The idea that the world's clocks could be altered, that time was not as uniform or absolute as it seemed. On the technical side, early leap seconds caused little trouble. Computers in the 1970s and 1980s were relatively simple, and timekeeping systems didn't rely heavily on continuous, uninterrupted timing. Networks were smaller, data less interconnected. A leap second was easy enough to insert into software and hardware. But as the world moved into the digital age, leap seconds would eventually become infamous, capable of crashing systems, disrupting servers, and confusing databases. That part of the story was still decades away in 1972. For now, the leap second represented a triumph of human ingenuity. It proved that we could build a timekeeping system that respected the ancient, irregular heartbeat of the Earth while also embracing the precision of quantum physics. It showed that humanity could thread a path between nature and technology. Most importantly, it marked a turning point in how we relate to time. Before leap seconds, time came from the sky. The heavens dictated the hours, the earth dictated the days, and clocks merely followed. After leap seconds, time became something we adjusted, corrected, and managed as needed. Time shifted from being a natural property to being a human-designed system that accounted for nature's imperfections. In that sense, the leap second was not just a technical invention, it was a philosophical one. It acknowledged that our planet does not turn with mechanical precision. It acknowledged that our machines, our satellites, our networks, our experiments require a kind of stability the Earth cannot provide. And it acknowledged that the best way to keep time for a living world is to accept that the world itself is not a perfect clock. When the first leap second ticked into existence, there was no global celebration, no countdown, no ceremony. It happened quietly, but it symbolized something enormous. The moment humanity fully took control of civil time, and the moment we began carefully negotiating with a planet that spins, wobbles, drifts, and surprises us. Predicting how the Earth will rotate may sound simple at first. You imagine a planet spinning in space, turning steadily like a massive, predictable wheel. But the real Earth doesn't offer that kind of simplicity. It behaves more like a system of coupled oscillations, influenced by oceans, winds, molten metal, seasonal cycles, and long-term geological changes. And because all these components interact, the rotation of the Earth becomes one of the most challenging things to forecast. Yet modern civilization depends on that forecast. Satellites orbit Earth with precise timing. global navigation systems require extremely accurate knowledge of how Earth's orientation changes from moment to moment. Communication networks rely on synchronized signals. Even the leap-second decision itself requires knowing exactly how far Earth's rotation has drifted from atomic time. To measure that drift, we need to know where Earth is pointing in space, not in a general sense, but down to fractions of a milliarc second. That's a level of precision equivalent to measuring the width of a human hair from several kilometers away, and that is exactly what the International Earth Rotation and Reference Systems Service, the IERs, does every day. The effort begins with a technique that looks almost like science fiction: Very Long Baseline Interferometry, or VLBI. VLBI uses radio telescopes located across the world, sometimes entire continents apart, to observe distant quasars. Quasars are among the most distant and stable beacons in the universe, billions of light years away. Because they're so far, their positions in the sky are effectively fixed. They serve as points of reference against which Earth's orientation can be measured. Here's how it works. Two radio telescopes, separated by thousands of kilometers, observe the same quasar at the same time. The signal from the quasar arrives at one telescope slightly before the other. The difference in arrival time depends on the orientation of Earth. By analysing this tiny time difference, on the order of nanoseconds, scientists can determine exactly how Earth is oriented in space at that moment. But that's only the beginning. Data from multiple telescope pairs across multiple continents creates a web of measurements that can map tiny variations in Earth's orientation, including the wobble of its axis and the length of its day. This method is extremely sensitive, so sensitive that it can detect changes in the Earth's rotation of microseconds. Alongside VLBI, another technique plays a critical role: satellite laser ranging. In this method, powerful lasers on Earth send pulses of light towards satellites equipped with retroreflectors, mirrors designed to send light back to its source. These satellites orbit the Earth precisely, often in nearly perfect geodetic trajectories. When the laser pulse returns, the time it took to travel round-trip is measured with astonishing precision. Because the speed of light is constant, the travel time directly reveals the satellite's distance. By combining data from multiple locations and many satellites, scientists can map the shape of Earth, its gravitational field, and how its orientation changes. GPS and other global navigation satellite systems add another layer of measurement. These satellites carry extremely stable atomic clocks. As they orbit Earth, their signals reveal tiny variations in Earth's rotation. If the planet rotates slightly faster or slower, or if its axis drifts, the timing and position of satellite signals shift in ways that ground receivers can detect. Large networks of GPS receivers provide a continuous stream of data about Earth's rotation and orientation. The IERs combines all these measurements: VLBI, satellite laser ranging, GPS, and more, and computes what are called Earth orientation parameters. These parameters include the exact rotation angle of Earth at any moment, the drift of the poles across the surface, the difference between atomic time and Earth rotation time, the small irregularities caused by atmospheric winds, ocean currents, and interior dynamics. These parameters are updated continuously, forming a global reference that keeps the world's clocks aligned with the planet. But if measuring Earth's rotation is already difficult, predicting it is even harder. The Earth is a non-linear system, meaning its components interact in ways that are difficult to model. A change in atmospheric pressure over the Pacific can influence wind patterns. Those winds can alter ocean currents. The ocean currents can redistribute heat. The redistribution of heat influences storms. Storms shift air masses. Air masses change angular momentum. And angular momentum affects Earth's rotation. This chain of events doesn't unfold cleanly or predictably. Instead, the climate system behaves chaotically. Small changes can produce large effects, and large changes don't always behave the same way twice. Consider the El Niño Southern Oscillation. During an El Niño event, warm water spreads across the central and eastern Pacific, altering atmospheric circulation patterns on a global scale. Trade winds weaken, jet streams shift, and vast regions experience changes in rainfall, storms, and temperature. These shifts in winds and atmospheric pressure transfer angular momentum between the atmosphere and the solid Earth, slowing or speeding the rotation by fractions of a millisecond. La Niña produces nearly opposite effects, strengthening the trade winds and altering ocean currents in a different direction. Both events change how Earth rotates, but not in perfectly predictable ways. Storm systems, especially large-scale circulation patterns, also influence rotation. A powerful storm can shift air masses thousands of kilometers. A season of stronger-than-average winds may slightly lengthen or shorten the day. Even seasonal snowpack contributes. Melting snow redistributes water toward the oceans, subtly adjusting Earth's moment of inertia. Volcanoes complicate the picture as well. When a major volcanic eruption sends ash into the stratosphere, it alters the distribution of heat in the atmosphere. This, in turn, changes wind patterns. Even though the mass of the ash itself is small compared to the planet, the climatic effects can modify atmospheric angular momentum enough to produce slight shifts in rotation. After the 1991 eruption of Mount Pinatubo, researchers observed changes in atmospheric circulation that affected Earth's rotation for several months. Then there is the atmosphere itself, an ever-shifting fluid with enormous mass. The atmosphere contains about 5 quadrillion tons of air, more than enough to influence Earth's rotation when that mass moves eastward or westward. Small changes in high-altitude winds or jet streams produce measurable variations. The subtropical jet, the polar jet, and seasonal monsoon systems all contribute. Because these systems are non-linear, their influence on rotation can be surprisingly abrupt. A sudden shift in the polar vortex or a change in the strength of the Pacific jet stream can modify the length of the day by tens or hundreds of microseconds. And that's only the atmosphere. The oceans are more massive and more complex still. Their currents operate on longer timescales, taking years to shift in meaningful ways. But their influence is profound. When warm water accumulates in one region or when a deep current strengthens, the redistribution of mass affects Earth's rotation. The oceans also exchange angular momentum with the solid Earth through tides and long-term circulation patterns. Underneath all of this lies the core mantle coupling. The outer core is a massive ocean of molten iron. It rotates at a slightly different rate than the mantle above it. Through magnetic coupling, viscous interactions, and gravitational effects, angular momentum is exchanged between the core and mantle. These exchanges can change Earth's rotation over years and decades. Some studies even suggest that oscillations in the core may be responsible for decade-scale variations in the length of the day. When you combine all these factors, the shifting winds, the churning oceans, changing atmospheric pressure, melting ice, volcanic eruptions, and the deep dynamics of the core, you get a rotation that is almost impossible to predict perfectly. Scientists build sophisticated models that incorporate climate data, atmospheric circulation forecasts, ocean observations, and geophysical measurements. But the predictions are never perfect. You might expect that Earth slows down gradually because of tidal friction, but in certain years, the Earth actually speeds up. During periods when atmospheric circulation shifts and moves large masses of air westward, the solid Earth gains angular momentum and rotates slightly faster. In recent years, the planet has experienced some of the shortest days ever recorded with modern instruments, evidence that even small shifts in global circulation can produce measurable effects. Sometimes the opposite happens. When the atmosphere speeds up in an eastward direction, Earth's rotation slows slightly. Major El Niño years often produce these effects. Long-term trends like glacial rebound also push Earth towards slower rotation as melted water spreads toward the equator. These competing processes, some accelerating, some decelerating, are the reason predictions fail. The Earth is not a clockwork mechanism. It is a system of interconnected, unpredictable motions, and even the best models cannot account for every future shift in winds or currents. If the Pacific jet stream strengthens unexpectedly, or if pressure systems reorganize suddenly, Earth's rotation changes in ways no model foresaw. Despite all this complexity, humanity has created a system that measures these changes with incredible precision. Instruments across continents, satellites in orbit, and atomic clocks in laboratories all contribute to a continuous portrait of how Earth spins. And yet the planet still surprises us. It slows down when models expect it to speed up. It speeds up when models expect to pause. It produces short days, long days, and irregular patterns that force scientists to revise their understanding. This unpredictability makes the leap second both necessary and difficult. Without measurements from VLBI, satellite laser ranging, and GPS, the drift between atomic time and Earth rotation time would be invisible until the mismatch grew too large to ignore. With them, the drift can be tracked precisely, but never predicted perfectly. Earth's rotation reflects everything happening on and within the planet: storms, seasons, ocean waves, molten iron currents, melting ice, volcanic ash, shifting winds, and the gravitational pull of the moon. It is a record of the planet's pulse, a constantly changing rhythm measured in microseconds. And behind every irregular tick of that rhythm stands the eye-ears, watching the sky and the Earth, stitching together the signals of quasars and satellites to understand a planet that never spins the same way twice. If you think of time as something stable, something that flows smoothly from one moment to the next, it can be unsettling to learn that enormous events on Earth, storms, earthquakes, melting ice, can alter the length of a day. Not in a dramatic, cinematic way. You will never wake up to find that a day has suddenly become an hour shorter, or that sunrise now happens at midnight. The changes are small, measured in microseconds and milliseconds, but at the precision at which modern civilization keeps time, they matter. The Earth is not a solid, unchanging sphere. It is a system of fluids, forces, and shifting masses, and when enough mass moves from one place to another, whether suddenly or gradually, it changes how the planet rotates. Angular momentum demands it, conservation laws require it, and time itself reflects it. One of the clearest demonstrations of this principle came in December 2004, when one of the strongest earthquakes ever recorded struck off the coast of Sumatra. The Sumatra-Andaman earthquake ruptured a fault stretching roughly 1,300 kilometers, an immense tear in the Earth's crust. It released a staggering amount of energy, equivalent to thousands of nuclear bombs. When that much mass shifts abruptly, the rotation of the planet shifts with it. Researchers studying the aftermath of the earthquake found that it had shortened the length of the day by a few millionths of a second. The redistribution of mass pushed some of Earth's material closer to its axis of rotation, much like a spinning figure skater pulling in their arms. This tiny change was imperceptible to human senses, but very real. Instruments designed to track Earth's rotation detected it immediately. It was a reminder that Earth's rotation is sensitive even to events deep underground. Earthquakes are dramatic, but they are not the only events capable of altering the planet's spin. Some of the most influential changes happen slowly, quietly, over decades. One of these slow changes comes from melting ice. When large ice sheets melt, water flows toward the oceans and redistributes mass across the planet. Ice near the poles is heavy, but located close to Earth's axis of rotation. When that ice melts, the water spreads into the oceans, which lie mostly at lower latitudes, farther from the axis. Moving mass outward increases Earth's moment of inertia, which slows its rotation slightly. Again, it is the same principle as a spinning skater extending their arms. The rotation responds. In the modern era, ice melt is accelerating. Greenland is losing hundreds of billions of tons of ice each year. Antarctica is shedding mass at an increasing rate. glaciers around the world are retreating. All of this adds water to the oceans and shifts mass outward. Over decades, this contributes to a gradual lengthening of the day. The effect is small, still measured in tiny fractions of a millisecond, but measurable through precise tracking of Earth's rotational dynamics. But just as melting ice pushes the rotation one way, other forces can push it in the opposite direction. Around the beginning of the 2020s, something unexpected happened. Instead of slowing down, as long-term trends suggested it should, Earth began to speed up. Days became slightly shorter. Not in any way a human could notice, just fractions of a millisecond, but enough that atomic clocks compared with Earth rotation time began to diverge more rapidly than usual. The difference was large enough to catch the attention of timekeeping institutions. The year 2020 produced some of the shortest days ever measured with modern instruments, and 2021 and 2022 continued that pattern. With Earth spinning slightly faster than expected, scientists began to ask why. The atmosphere had been shifting, the oceans had been circulating differently, climate variability was playing a role, but the exact combination of factors was uncertain. Some researchers suggested that long-term oscillations in Earth's core might be involved. Others pointed to changes in atmospheric pressure patterns. A few studies noted that the long-term redistribution of water across the planet through rainfall, drought, and ice melt may have contributed to the shifts. The precise cause was not obvious. What was clear was that Earth had entered a phase of unexpectedly rapid rotation. As this acceleration continued, a remarkable possibility emerged. For the first time in history, the world might need to remove a second from coordinated universal time. A negative leap second. This was a reversal of everything the world had been doing since leap seconds were introduced in 1972. Until then, Earth had always been slower than atomic time, requiring leap seconds to be added. But if the planet rotated fast enough, the atomic clocks would get ahead of Earth rotation time, and a leap second would have to be deleted. For timekeepers, this was more than a curiosity. It was a practical and philosophical problem. Adding a second is easy enough. Computers, networks, and timing systems are already designed to handle the extra moment. But removing a second, skipping straight past a number that should have existed, creates complications. Many systems assume that time moves forward without missing values. A negative leap second would break that assumption. Imagine counting upward by seconds. 57, 58, 59, and then immediately, without any transition, the clock becomes the start of the next minute. It is simple to speak aloud, but difficult for software to represent. Some software systems store time as a count of seconds since a reference point. If a second is missing, it violates the structure of the time sequence. Databases, servers, financial systems, and communication networks would all need to know how to handle a moment that does not exist. Because of this, some scientists and engineers have argued that negative leap seconds should never be used. They believe that if Earth begins running too fast, timekeepers should let the difference accumulate more naturally rather than forcing a correction that could break global systems. Others argue that negative leap seconds are necessary if the goal of coordinated universal time is to remain within 1 second of Earth rotation time. Without them, UTC would drift away from UT1, and if that drift continued, civil time would gradually become disconnected from the position of the Sun. The debate reveals something deeper than technical preferences. It shows how modern timekeeping is shaped not only by physics, but by human priorities. Earth's rotation is not stable, atomic clocks are. But humans live according to the Sun, and the leap second, whether positive or negative, is humanity's way of balancing those realities. The acceleration in Earth's rotation during 2020 to 2022 raised questions not only about leap seconds, but also about the climate system. If atmospheric circulation changes suddenly, Earth's rotation responds. When the oceans move vast currents of water, the rotation adjusts. These events are measurements of how the planet is behaving on scales too slow or too subtle for day-to-day experience, but easy to see in the data that timekeepers monitor. Changes in Earth's rotation become a kind of indirect record of global processes. A prolonged El Niño alters wind patterns across the Pacific and redistributes atmospheric momentum. A shift in the jet stream causes the solid Earth to adjust its rotation. Major oscillations, like the Arctic Oscillation and the North Atlantic Oscillation, rearrange pressure systems, feeding angular momentum into the atmosphere and affecting the length of the day. None of these influences work alone. They overlap and interfere with each other. A strong El Niño may shorten the day. A La Niña may lengthen it. A volcanic eruption may alter atmospheric heating. Long-term ice melt shifts mass outward and slows the rotation. Short-term wind patterns add and remove angular momentum almost constantly. And beneath everything, the core continues to rotate at its own pace, slightly decoupled from the mantle above it. The result is a complex multi-layered system where Earth sometimes speeds up and sometimes slows down, and where the direction of the change depends on countless variables interacting across the planet. These changes are tiny, but they accumulate, and the world's timekeeping system must account for them. The leap second was created for this reason, to bridge the gap between the perfect march of atomic time and the wandering rotation of the Earth. But as the planet enters periods of accelerated rotation, new questions arise about how long this system can continue. One thing is clear: Earth's rotation is not static. It never has been. It is a living measure of what the planet is doing, of winds shifting, currents swirling, ice melting, and the deep interior moving with forces no human can see directly. And sometimes those changes are strong enough to alter time. For most of human history, the idea of adding or removing a single second from the world's clocks would have meant nothing. A second was a blink, a breath. It had no machinery behind it, no system, no network. Time was something you glanced at on a wristwatch or heard from a church bell. But the digital world changed that completely. When the leap second was introduced in 1972, almost nobody imagined a future in which the entire planet depended on perfectly synchronized clocks. They didn't imagine global computer networks, financial systems trading in microseconds, GPS satellites broadcasting continuous timing codes, or cloud servers needing exact alignment to avoid corruption. A second was still just a second. Then the world connected itself, and that harmless extra second, the small adjustment meant to keep human time aligned with Earth's rotation, became a troublemaker. Computers do not experience time the way humans do. They don't look at clocks or watch seconds tick by. Instead, they track time using internal counters, often by counting how many seconds have passed since a specific reference moment. One common example is Unix time, which counts every second since January 1st, 1970. This design works beautifully, unless a minute suddenly contains 61 seconds. For a computer, this looks like a violation of reality. It's as if a number repeated itself when it shouldn't, or a moment existed twice. Some systems freeze when that happens, others crash. Some interpret the repeated second as time going backward, which confuses programs that expect time to always increase. This was exactly what happened during the leap second added on June 30th, 2012. As clocks around the world approached midnight UTC, the extra second was inserted, and thousands of systems didn't know what to do with it. The result was a cascade of failures. Large airline reservation systems went down. Servers froze. Databases locked up. Websites slowed or vanished. And most famously, Reddit crashed so hard that engineers spent hours scrambling to bring it back online. The problem was simple. Some operating systems, especially older versions of Linux, weren't built to handle a minute that didn't follow the normal rules. Their internal clocks encountered the repeated second, panicked, and spun into high CPU usage or full lockup. It wasn't limited to 2012. The 2015 leap second caused similar issues. Some cloud services experienced slowdowns, some networks had delayed traffic, a few financial systems had to halt automated trading for safety, Even though engineers knew the leap second was coming, and even though the world had been through this before, the fundamental design of timekeeping in computers made the problem difficult to avoid. The challenge lies in how deeply time is embedded into everything. A database uses timestamps to keep track of transactions. A server uses them to coordinate distributed processes. A network protocol uses them to organize packets. A file system uses them to record when files change. A programming language library uses them to schedule operations. If time is off, or duplicated, or suddenly jumps, all these systems feel it. Something as tiny as 1 extra second can ripple across global infrastructure. Which is why many large technology companies eventually decided we're not doing this anymore. They didn't eliminate leap seconds. That decision belongs to organizations like the IERs, but they stopped applying them in the traditional way. Instead of inserting the extra second all at once, they smear it. Time smearing means spreading the extra second over a longer period, making the entire day run just a fraction slower so that the last second never becomes a strange 61-second minute. It's like smoothing a bump into the road instead of making drivers hit it head-on. Google was one of the first to implement this. They introduced a leap smear that stretches the length of each second ever so slightly across several hours. Instead of adding 1 second at midnight, they distribute the correction over a window of many hours, adjusting each second by a tiny fraction. To a human, the clock appears completely normal. To a computer, it never encounters the illegal repeated second. Amazon and Meta later adopted similar strategies. Each company uses its own method. Different smear windows, different mathematical approaches, but the idea is the same. Smooth out the leap second so that software never sees a discontinuity. This creates a strange situation. During a leap second event, not every company is running on exactly the same time. Their clocks disagree by small fractions of a second, and for most applications, that's fine. Modern systems are built to tolerate tiny timing differences between networks, but it underscores the difficulty of reconciling digital precision with planetary irregularity. The leap second was created as a gentle correction for humans, but humans don't feel it. Machines do, and machines are uncompromising. This tension quickly became part of internet culture. Whenever a leap second was announced, jokes spread online. The internet is going to break again. Prepare for the 1 second apocalypse. Shut down your servers. The 61st second is coming. Memes circulated about time loops, computers panicking, and programmers taking the day off. Some joked that it was the one moment each year when time travel was possible because the clocks repeated themselves. Others used it as an excuse to blame outages on that annoying extra second. Behind the humour was real anxiety. Engineers dreaded leap seconds. Network administrators prepared for them like meteorologists preparing for a storm. Even though only a small number of systems failed, the failures were dramatic enough to shape the reputation of the leap second as a troublemaker. The irony is that leap seconds were created as a simple, elegant way to keep civil time aligned with Earth's rotation. They were never meant to interfere with technology, but as computers became the backbone of civilization, the leap second transformed from an astronomical adjustment into a computational hazard. Some systems still handle leap seconds correctly, others ignore them, many smear them, and some avoid them entirely by running clocks several seconds ahead or behind UTC and converting only when necessary. 1 second should not be powerful enough to break parts of the internet, but it is. It's a reminder that time, which seems effortless in daily life, is one of the most delicate and complex systems ever engineered. A single extra second exposes the hidden machinery behind everything we do, from airline reservations to cloud services to social networks. And when that machinery hiccups, the world notices. For half a century, the leap second served as a quiet reconciliation between two different forms of time, the perfect beat of atomic clocks and the wandering rhythm of Earth's rotation. It was a compromise crafted to keep civil time aligned with the world we live on. But compromises are fragile, and the leap second has never been universally loved. It was tolerated, useful, scientifically elegant, but troublesome in practice. By the early 21st century, as global systems became more interconnected and more dependent on uninterrupted timekeeping, the leap second began to look less like a graceful adjustment and more like a recurring source of risk. Computers struggled with it, networks stumbled, engineers dreaded it, and as Earth's rotation entered a strange period of acceleration in the late 2010s and early 2020s, the possibility of a negative leap second, a deletion of time, made everything even more precarious. The tension finally reached a breaking point in 2022, when representatives from major nations and international organizations gathered at the General Conference on Weights and Measures. After decades of debate, they voted to eliminate leap seconds altogether by 2035. It was a historic decision, and in a sense, it marked the end of an era. For the first time since the invention of UTC, the world agreed that civil time no longer needed to follow Earth's rotation so closely. We were beginning to let go of the planet's natural rhythm. To understand why the decision happened, it helps to look at who pushed for it. Most of the world's large technology companies supported eliminating the leap second. Google, Amazon, Meta, and many others had spent years wrestling with the technical chaos leap seconds caused. Distributed systems, which depend on continuous time to coordinate tasks across thousands of servers, don't cope well with sudden discontinuities. Finance companies worried about millisecond-level precision in global trading. Cloud platforms feared outages. Navigation systems required stable timing codes. The leap second disrupted all of these things. Even governments with sophisticated timekeeping infrastructure saw the leap second as a growing liability. Every time a leap second approached, national laboratories had to prepare for it. Critical systems had to be tested. Global coordination was required. And even then, unpredictable failures appeared in systems no one had expected would be affected. The issue wasn't the leap second itself. It was the modern world's dependency on precision. A single added second exposed weaknesses in software frameworks, databases, and hardware. It made global timekeeping fragile. But the greatest concern wasn't about positive leap seconds. It was about negative ones. When Earth began spinning slightly faster around 2020, scientists realized that, for the first time, atomic time was falling behind Earth rotation time. If the trend continued, timekeepers would eventually need to remove a second from UTC, skip a second completely. Instead of an extra second at the end of a day, that day would simply lack a moment that should have existed. For humans, that's easy enough to imagine. For machines, it's a contradiction. A missing second is far more damaging than a repeated one. Software that relies on continuous time would suddenly encounter a gap. Systems that schedule tasks would be confused. Global synchronization protocols would encounter a moment that cannot be represented. A repeated second can be handled with effort. A missing second breaks fundamental assumptions. Large nations agreed that a negative leap second was likely impossible to implement safely. The risk was too great, and the effort required to redesign global systems from the ground up was unrealistic. So the choice became stark: either reinvent the entire digital infrastructure of the planet or retire the leap second. The vote in 2022 reflected the practical answer. Eliminate the leap second by 2035. Let UTC drift. Stop forcing atomic time to accommodate the planet. Stop trying to correct the Earth. From a technical perspective, the decision made perfect sense. From a philosophical perspective, it raised profound questions. One question echoed throughout scientific circles. Are we choosing atomic precision over planetary reality? For thousands of years, humans lived by the sky. Noon was the sun. Midnight was the midpoint between sunsets. Days were anchored to Earth's rotation. Even when mechanical clocks emerged, they still followed the sun. Time was a reflection of the cosmos. The leap second was humanity's way of preserving that connection. Removing it represents something different, a decision that nature's irregularities no longer matter for civil life. Our machines, our networks, and our satellites have become the dominant force shaping time. The planet's rotation, once the most fundamental reference point for all of human history, is now secondary. What does that mean for civil time? As UTC drifts away from Earth's rotation, the Sun will no longer align neatly with the clock. At first, the difference will be tiny, a second after a few years, a minute after many decades. Most people won't notice. Society will continue, daily life will remain unchanged. But over centuries, the drift will become impossible to ignore. If Earth keeps slowing on long timescales, and history suggests it will, noon on the clock will eventually occur when the Sun is no longer overhead. Not slightly off, very off, hours off. A person centuries from now could look up at the sky at 12 noon and see the Sun sitting far from its expected position. Civil time will no longer trace the sky. It will trace the atoms. This disconnect is not immediate. It accumulates slowly, almost invisibly. But when people imagine timekeeping in the far future, they sometimes imagine a more dramatic adjustment, a leap of hours rather than seconds. If UTC drifts far enough, timekeepers may someday introduce a leap hour, shifting civil time forward by 1 whole hour to realign the clocks with the Sun. A leap hour would be rare. Perhaps once every few centuries, maybe once every 1,000 years, but it would mark a moment when society collectively resets the relationship between clock time and solar time. The idea feels surreal today, but it follows the same logic as the leap second. If small corrections become too disruptive, you make fewer but larger corrections. There is beauty in the idea, in a strange way. Instead of nudging time every few years by a second, the future might contain occasional ceremonial adjustments, moments when society acknowledges how far atomic time and Earth time have drifted apart and decides briefly to reconcile them. But leap hours remain theoretical. What is certain is that civil time will slowly drift away from Earth's rotation. Once leap seconds disappear, the clocks will not follow the planet. They will follow physics. This decision marks a profound shift in the story of time. For thousands of years, nature dictated time. For the last 50 years, timekeeping tried to serve both nature and technology. Now, the future belongs to atomic precision. It is a quiet revolution, not celebrated, not marked by countdowns or ceremonies, yet it reshapes one of the deepest human concepts. When future generations look back at the history of time, they may see the leap second not as a permanent fixture, but as a transitional chapter. A half-century during which humanity negotiated between the sky and the atom, between tradition and innovation, between Earth's rotation and the needs of a global digital civilization. The end of the leap second is not the end of timekeeping. It is the end of the idea that time must always follow the planet. In its place, a new idea emerges. Time will follow what humans create, measure, and choose. The Earth will continue to wobble, drift, slow, and speed up, as it always has. But the clocks on the wall, and the clocks in orbit, will no longer wait for it. When you look at a clock that reads 12 noon, there is an unspoken expectation about what that means. It is a moment built into human intuition. The middle of the day, sunlight overhead or somewhere near it, the natural pause between morning and afternoon. Even in an age of electric light, screens and 24-hour schedules, the idea of noon still carries a physical sense, a connection to the sun. But a future without leap seconds slowly unties that connection. UTC will continue ticking with atomic precision. An unbroken stream of perfect seconds, each identical to the one before. Earth will continue rotating with unruly, organic irregularity, sometimes slowing, sometimes speeding up, always influenced by winds, currents, melting ice, the moon's pull, and the churning motion of the core. Without leap seconds, those two systems, atomic time and planetary rotation, will no longer be stitched together. They will drift apart. Very slowly at first, then noticeably, then profoundly. In the first few decades, the drift is almost imperceptible. A second difference here, a few additional seconds there. most people will never notice, just as most people today barely notice the leap seconds themselves. But the drift accumulates. In the span of a human lifetime, it can become something you feel. Timekeepers model this drift by projecting the long-term deceleration of Earth's rotation. Tidal friction from the Moon continues to remove angular momentum from Earth, lengthening the day by a tiny amount each century. Historically, the average increase in day length has been roughly 1.7 milliseconds per century. That seems absurdly small, but atomic time is sensitive to absurdly small. By the year 2010, UTC may be tens of seconds ahead of Earth rotation time if no leap seconds are ever added again. Noon on the clock will arrive while the sun is still slightly climbing or descending, not dramatically wrong, but subtly off from where it once would have been. By the year 2200, that offset grows into the realm of minutes. A person checking the clock at 12 o'clock might notice that the sun no longer feels central in the sky. It might be slightly east or west, depending on local longitude and seasonal tilt. The older pattern, when clocks and sunlight lined up almost intuitively, will begin to feel weaker, more abstract. The drift continues. By the year 2500, if long-term models hold and Earth continues its millennial-scale deceleration, UTC could be an hour or more away from solar noon. A civilization living in that era might look at the clock and see 12 o'clock noon in a bright morning, or in the late afternoon, or under the orange glow of a setting sun. In high latitudes and certain seasons, it may even occur in darkness. There is something strange and almost poetic about imagining a world where the meaning of noon has drifted so far from its astronomical roots. The word itself will not have changed, the clocks will not look different, but the sun will no longer care. This is the natural consequence of choosing a purely atomic definition of time. When atomic time and Earth time were coupled through leap seconds, the drift remained tiny, a second here, a second there. Without them, the drift becomes a long, gradual unwrapping of civil time from the planet. But the story is not as simple as Earth slows forever. For centuries, that was the expectation. Tidal friction from the Moon is constant and relentless. It acts like a brake on Earth. The Moon recedes by about 3.8 centimeters per year, roughly an inch and a half, and that recession lengthens the day. This long-term trend is visible in ancient eclipse records from Babylonian, Chinese, Arab and Greek astronomers. Their observations show that Earth rotated faster thousands of years ago. But on top of this long-term slowing are other influences that can speed up or slow down the rotation unpredictably. Climate variability plays a role. Changes in atmospheric circulation redistribute angular momentum. Shifts in deep ocean currents do the same. Melting ice changes the distribution of mass. Even the fluctuating behavior of the fluid outer core can modify rotation on multi-decadal scales. This means the future drift is not a perfect line. It may flatten, it may accelerate, it may reverse direction for years at a time. The unexpected acceleration of Earth's rotation between 2020 and 2022 showed how fragile long-term assumptions are. That brief period produced some of the shortest days ever measured, something almost no one predicted. If such accelerations became common, the drift between UTC and solar time could shrink rather than grow. In fact, some geophysicists have proposed that the recent acceleration could be part of a multidecadal oscillation linked to the core. If so, Earth might experience periods of faster rotation again, or slower, or both in cycles. The result is a future that is scientifically knowable in broad strokes, but not in precise detail. Even so, the general trend over centuries rather than decades leans toward Earth slowly losing angular momentum, meaning that atomic time will pull ahead. This raises a question that feels almost philosophical. What happens to civil time when it no longer reflects the sun? The answer depends largely on human preference. For much of history, timekeeping was anchored to the Earth's rotation because nothing else existed. When atomic time arrived, humans adapted, but they kept that connection through leap seconds. The removal of leap seconds is a shift in that relationship. It marks the moment when humanity decided that precision and practicality mattered more than fidelity to the sky. As centuries pass, the drift will grow too large for people to ignore. When UTC is 30, 40, 50 minutes ahead of solar noon, a sense of dissonance may emerge, especially in cultures that still associate daily rituals, prayer times, or work cycles with the position of the sun. At that point, a correction becomes necessary, not a leap second, but something larger, the concept of a leap hour. A leap hour is the logical successor to the leap second in a world without small corrections. Instead of inserting or deleting a second every few years, a leap hour would be implemented perhaps once every several hundred years to realign the clocks with the sun. The correction would be abrupt, but rare enough that no digital infrastructure would need to constantly support discontinuities. Imagine a future society being told, at midnight on the first day of the year 2488, the clocks will move forward by 1 hour to realign civil time with the position of the sun. It would be ceremonial, memorable, and disruptive for only a moment. Children might recall it as a historical oddity. Adults might adjust their schedules. Technologies would be updated long before the event, and then life would continue, now realigned with the sky. Such a leap hour preserves a kind of long-term truth. Civil time still follows the Earth, but on scales appropriate for a civilization whose systems cannot tolerate yearly corrections. It is entirely possible that future rationalizations of time will settle into this rhythm, small drifts accumulating quietly for centuries, punctuated by a rare collective reset. But there is another possibility, one that drifts even farther from the traditional meaning of time. Humanity may eventually stop caring whether noon aligns with the sun at all. Time might become a fully human construct, unmoored from astronomical origins. The sun may become irrelevant for scheduling. Future societies might treat solar time the way we treat the lunar calendar, meaningful, interesting, but not operationally central. In that world, clocks would not need leap hours. The drift would be allowed to continue indefinitely. Noon would migrate across the sky, through dawn, into the night, through the morning again, completing a full cycle every few thousand years. Eventually, 12 o'clock noon could occur in total darkness, not because something is wrong, but because time has evolved into something completely human-made, something independent of Earth. This idea sounds remote, abstract, almost alien, and yet it flows naturally from the decision to remove leap seconds. Once the connection to planetary rotation is broken, civil time becomes a creation of atomic physics alone. Time becomes something defined not by the sky, but by the measurement systems that surround modern civilization. The future without leap seconds is not dramatic. It is not something anyone alive today will see unfold fully. It is slow, steady, almost geological. But it represents a quiet shift in how humanity relates to the universe. Time begins to drift, not because of chaos or failure, but because of a choice. The decision that precision, stability, and technological harmony matter more than aligning the clock with the sun. Civil time becomes atomic time. Planetary time continues on its own path. And between them grows a widening distance measured not just in seconds, but in meaning. When people talk about time, they often describe it as though it were something exact, something that flows like a perfect river, steady and unbroken. We design clocks that tick with precision so fine they can measure the slight gravitational difference between a tabletop and the floor beneath it. We speak of nanoseconds as if they were stones we could put in our pockets. We strive for regularity, certainty, and a sense that every second is equal to the one before. But the world beneath us has never shared that ideal. The Earth does not rotate with mathematical purity. It shivers in the atmosphere's breath, swells with the movement of water, trembles during earthquakes, and bends under shifting ice. It speeds up, it slows down, it wobbles, it stirs with the forces of the moon and the sun. It is a living planet, a fluid planet, not a machine. And so the time we experience, the time written into day and night, carries the imprint of that restlessness. The contrast between human precision and Earth's imperfection reveals something very old and very human. We crave order, we want patterns, we want the universe to behave in ways we can write down, codify, program, synchronize, and rely on, not because we are rigid creatures, but because precision lets us build things together. It lets satellites navigate, lets telescopes observe, lets global networks talk in harmony, lets memories be stored and retrieved. Precision is not a cold desire, it is a social one. It is the scaffolding of cooperation. And yet, for all our tools and definitions, we still live on a world that refuses to obey the straight lines we draw. The Earth is messy, it is dynamic, it is shaped by molten currents deep below and by invisible currents above. It flexes beneath the weight of oceans, it adjusts to every breath of wind. Its rotation carries the signatures of storms, volcanic eruptions, El Niño cycles, ancient tides, and the slow unspooling of geological time. Everything about the planet is in motion, even the motion itself. There is a kind of poetry in that, a planet that will not keep a steady beat, and a species determined to measure its heartbeat anyway. When humans invented atomic clocks, we created something the Earth could never provide: absolute regularity. A tick defined not by rotation or orbit, not by weather or seasons, but by the energy transitions of atoms. These clocks do not drift, they do not wobble, they do not care about oceans, winds, quakes, or ice. They have no memory of storms, no sense of seasons. They are immune to everything except the laws of quantum mechanics. They are perfect in a way nothing natural can match. And yet we still live on this planet, not inside an equation. We walk on ground that tilts and sways. We watch the sun arc across the sky because the Earth's rotation draws that arc for us. We feel the day as a physical thing, not a mathematical coordinate. Timekeeping became a negotiation between the world we inhabit and the tools we build to understand it. For thousands of years, human beings lived entirely by planetary time, the position of the sun, the movement of shadows, the length of days and seasons. Even after clocks were invented, their purpose was to mimic the heavens. The clock was a reflection of the sky. Midnight was the midpoint of darkness. Noon was sunlight at its highest. Then, without fanfare, without any cosmic announcement, the meaning of time shifted. Atomic clocks entered the world. A new kind of time appeared, one that flowed smoothly even when the Earth did not. For a while, we tried to keep them linked. Leap seconds were our compromise, a gesture toward nature, a way to acknowledge that even a planet's imperfections deserved respect. But as the digital world expanded, the imperfections became liabilities. They crashed servers. They confused software. They revealed the hidden fragility of global systems. And so humanity chose to let atomic time run as it wished, without waiting for the Earth's wandering. This choice did not break our connection to the planet, but it transformed it. Time remained something we live through, something we feel, but it also became something engineered, something designed for the functioning of modern civilization. We correct the planet with atomic clocks. We adjust the definition of a second based on quantum transitions. We tell Earth that its rhythm is beautiful, but not sufficient for our needs. There is something humbling in that, and something bold. It is not arrogance. It is adaptation. We live in a universe where nothing is perfectly regular. Not planets, not stars, not galaxies. Even the orbits of the planets shift over eons. Even the moon slowly drifts away. Even the spin of Earth, which feels eternal, is just a transient arrangement of mass and momentum. And yet, the human mind reaches for precision that the universe does not offer on its own. We build a framework the cosmos cannot supply. We create order in a world shaped by fluidity. We measure the wobble beneath our feet and fold it into a system that can coordinate billions of people. Time becomes a dialogue between what is and what we choose to define. There is a quiet beauty in recognizing that the planet itself carries a history of imbalance. The rotation slows under the moon's pull, speeds under sudden atmospheric shifts, stutters under earthquakes, swells and contracts with ocean currents, and dances with the faint motion of its molten core. Each tiny variation is a signature of something physical, something real, a whisper of a storm, a memory of melted ice, a trace of deep interior motion. Every second we add or remove, every calculation we make about leap seconds or the drift of UTC reflects the fact that this planet is alive in its own geological way. And for all our desire for perfect time, we still stand on ground that trembles faintly with the movement of the deep layers beneath us. There is something grounding in that, something human. The most advanced technologies ever created depend on an idea of time born in laboratories, defined by atoms stabilized by physics. Yet the body still wakes to sunlight, the sense of a day still follows the sky, and the meaning of time still rests in how we move through it. No amount of precision replaces the simple human feeling of morning light, or the way dusk settles, or the rhythm that sleep and wakefulness trace through each day. We may measure time with atoms, but we live it with senses shaped by the spin of the earth. The imperfections of the planet do not diminish that, they enrich it. The wobble beneath our feet is a reminder that we inhabit a world in motion, that time is not a straight line drawn across the universe, but a collaboration between physics, geology, climate, and human intention. Every clock, every satellite, every timestamp in a database is connected, in some distant but real way, to the rotation of the Earth and the forces that reshape it. And every adjustment we make, whether adding a second, smearing it across hours, or someday inserting a leap hour, is part of our ongoing attempt to harmonize our tools with the shifting world beneath them. Time is not just a measurement. It is an agreement, a negotiation, a story of atoms that tick with perfect regularity, and a planet that turns according to the restless physics of oceans, air, and molten iron, and a species that stands between them, trying to listen to both. It is the story of a world that wobbles, and a humanity that learns how to measure the wobble without being defined by it. It is a reminder that precision is a human creation, and imperfection is part of the Earth's nature, and time, real time, is the meeting point between the two. And as you sit here, listening, breathing, feeling the weight of your own body on the ground, you are sharing in that meeting point. You are part of the same planet that trembles, tilts, drifts, and dances through space. You are living inside a world whose rotation is never the same from one day to the next. And yet, somehow, life finds rhythm. Humans find meaning. Seconds find their place. Time continues, imperfect, precise, and profoundly human.